Hi. In this video we now take a closer look how to do with R this sort of a classical statistical test like t-test and f-test. So this is a situation where we have let's just say some numerical random variable y, and then there's for example some variable x which divides the whole population into two parts, so that we have kind of two population called A and population called B, and in that sort of a case we want to test is the population means in these two populations equal or not. And that's really the classical two population t-test situation. For two population t-test situation, we kind of assume that this sort of a population variance, that means the dispersion, is same level in these two subpopulation A and B. Sometimes this population, this variance can actually be in a different sides, and that's why we may sometimes use this sort of a function called var-test to test if the population variances are equal or not. And this is giving us this sort of a f-type of test statistics. And so the t-test was this classical test for testing the population means are they equal or not. But it assumes in a classical situation that these population variances are equal. However, if we now come to the conclusion that these population variances are not equal, and under that condition we still want to continue to research whatever the population means are equal or not, then we can use what is called as a Wells t-test by using this sort of a function with argument var equal false. Then all these things what we have talked about here basically are related to the normal distribution, so that we kind of assume when we are doing the t-test or Wells t-test that this random variable y in both of these subpopulation A and B should follow normal distribution. However, if it's really clear that there is no normality in or the random variable y does not follow normal distribution, then we may consider, but let's just say that random variable y does not follow the normal distribution but still is this sort of a numerical variable. Then we can use this sort of a Wilcoxon test, which is also called as a Mann-Whitney test. It is this sort of a non-parametric test which tests whatever the two, let's just say, population medians are in the same level or not. In R, I have here done some few examples, and these examples are really, or this example code actually, this is really about first generating just from normal distribution with normal distribution with the population mean 5 and population variance being 4, generating 23 observation, and then generating the population B, which is having this sort of a form, that is population mean is 7 and population variance 2.5 raised to the power 2. And so that these values are like realization from two different populations, from population A and population B, and if I put them by using this C function as together, then we have this sort of a y vector, and then we can use this sort of a x vector to denote from which population these values are coming from, and we can use here the rep function to come up with the solution. And then if we use the t-test, we get this sort of a print or output, and here you can find that this is actually the test statistics, this minus 2.2893, and then there's a p value which is quite small now, and this would mean that we would now reject the null hypothesis that the population means are equal. That is based on these sample values which we have here in vectors yi and yp. They are on they sample means are so much far apart that based on this we make a inference that yes, the population means should also diverge from each other. Of course, we know here, because we have generated this data from this sort of a population means, like 5 and 7, we obviously beforehand know that there is actually difference. However, when we think about the true situation, we only have this y vector values, and then we have to, without knowing, make an inference, is this population means in the same level or not. And so by using this sort of argument or during the dollar sign and word statistics, we can get the statistics value out of this, so the statistics, and a p-value can be obtained by using this sort of a code. If we start to think about it, is the variances, this population variances, are they in the same level or not in these two populations A and B? And here we have done this what is called a VAR test, and you can use this sort of formula way of doing it. And here it is tested if in these two populations the ratio of sample variances let's say that is the true ratio of variance equal to 1 or not. And when we take the sample variances and look what is their ratio value, we get this sort of a value. And then it can be shown that it is still that sort of a value that we are not so guaranteed, that we are not so safe sized to say that the population variance would diverge. So here the result is that the null hypothesis, what is that this population variance equal size, would hold. We of course know that population variance, they are not actually equal. So this is a population variance at 2 raised to the power 2, and this is 2.5 raised to the power 2. So there's a slight difference. However, when we are looking at this data which is given in here, or what sort of data we have here obtained by this simulation, that value is really, those values are such, the realization are such that based on those values we cannot be certain, or let's just say without possibility of making a wrong kind of decision, there's not enough really difference in sample variances that we would reject the idea of population variance being equal. So here basically we would assume that the population variance are equal, and then we could make the inference based on if we wanted to consider those the population means, that we can just use this t-test which we were using here to make our inference about is the population means equal or not. However, if for some reason we think that regardless of what this test says, that we know or we believe those variances are not equal, then we can test the equality of population mean by this Wells two-sample t-test, and then we can again use this sort of a t-test, but this time we must be this argument var equal denote as a false. And here's the test statistics. Here's now actually test statistics the same as the previous cases. It's well, has it really changed? Yes, it has actually changed a little, but sometimes it can be actually same. Well, depends on what is the sample size really, but usually the p-value changes some sense. It can go down or up, depend on how much the variances are different from each others. And so we come up with this conclusion still by using the Wells t-test that the population means are different. If we make a inference based on using the significance level, this classical significance level of 5%. So the p-value here is less than 0.05. So we would, let's just say this sort of a classical way of making inference. We would just make a recommendation or the decision that yes, there is enough evidence in this sample means to show that the population means must also diverge from each other, so the equally does not hold. And lastly, we have done here the Wilcoxon's test, which is called as a Mann-Whitney test, probably more usually known. And here's the statistics we don't really need to worry about, and here's the p-value. And because this test is not as powerful as the t-test, this test basically says that we don't have really enough evidence if we are making a inference with choosing the significance level to the 5%, then based on Wilcoxon's test value, we would still consider that these two populations are on average on equal level. So let us go to the R and do the same thing quickly by using this code. And this time around, when we generate this sort of data, they look different than in our example case. So this data is not the same what was used here in these slides. So our results will now be different compared to what was given here. So if we, for example, now do the t-test, the classical t-test with equal, we get this sort of a result, which now p-value is not anymore below 0.05 level. So we would actually here in this dataset case show that, or see that that these sample means are not so far away, so that we are not exactly certain to reject the null hypothesis. So even if we are now generating the observations from the same population where we actually know that the population means are different, but if the population means are quite close, we can then come up with these sort of a sample means that are not so far away from each other because of the randomness. And then sometimes we get this sort of a result. I should be noted now that this test can be sent to same result can be just obtained by if we have these two population vectors like this way, then we get exactly the same result. So regardless of does we use this sort of a formula way of giving us the data. So these are the same things. And so the statistics, the value of t-test can be obtained by like here, and the p-value can be obtained by using this type of code. And the var test is like given here. So this time around, yes, we would still argue that there's not enough evidence to say that population variance would not be equal. So null hypothesis that population variance in these two populations are equal would hold. So this is not really based on so that if we take the variance for this A population and variance for B population and we take that means the sample variance. And if we now take the ratio of these two values like given here, surprisingly that's the ratio of our variance, and that's actually the F-test used here. So in this sort of variance test, the F statistic is actually ratio of these sample variances. And now we can continue. However, if we have this sort of result, we can still look for how the Wells-T statistic would be given at what sort of a result it would given us. And this is the end result for Wells-T statistic as far as the p-value is concerned. And lastly, if we do take the Wilcoxon's test, which is now surprisingly giving us the p-value which is different. So this is a really bit strange actually. But let's not go to the details, because that obviously can happen. But usually it goes other way around. So that the Wells t-test or classical t-test can say that there's a difference, statistically significant difference in population means. However, Wilcox-Ransom test can, in many cases, says that even those cases when t-test would reject the null hypothesis, in Mann-Whitney test case it would just hold. The null hypothesis would hold, that is, the population means are equal, so that there's not enough evidence to show that they are not. But this is actually other way around this case happens, and it is possible to go other way around. So that's not really there's not this sort of order always. So this case, this is I guess, more rare example where the Wilcoxon's, that is a Mann-Whitney test, is able to reject the null hypothesis when it truly should be rejected, because we know the population means are different, and in the same time, t-test is not really giving us the right sort type of result. Having said that, this does not mean that you should always use this Mann-Whitney type of test. On the contrary, you should continue to use the t-test and Wells t-test first, and if there's just clearly evidence of not normality holding, then we can go for this sort of a non-parametric test. What t-test which we were just covering up can be now generalized to the more general case where we have a more subpopulation rather than just two, and that is called one-way analysis of variance. And in one-way analysis of variance, we basically creating these sort of a linear models and what could also sometimes call as another type of models. So in R, when we are performing this sort of analysis of variance, we need to use this sort of a function at some point. And once we have, so to create these sort of a linear models and so on. So in analysis of variance, the idea is that we may have let's just say k amount of subpopulation, which is now denoted by 1, 2, and so on. Of course, we can use, like in our code, we are using here A population, B population, C and D population in our example case. However, the idea is to test, is this sort of a null hypothesis true or not? Meaning that is in this subpopulation defined by this our x variable, is the sample means in the same, the population mean in the same level in all subpopulation. And if that holds, then we say that x does not have an effect on average values of y. However, if for some population or some subpopulation the population means diverges from others, then we would reject this null hypothesis and we would say that the x variable has an effect on the average level of response variable. And in order to do this sort of analysis of variance in R, we first have to use either LM or V functions to create these sort of linear models. Then we can use this sort of ANOVA function to perform the actual test statistics for testing these sort of things. The F statistic and F test, there's a assumption that variances are equal in all subpopulation, and we can use this sort of a Bartlett test to test is this homogeneity of variance equal. If it's not equal, then we can use this sort of a function one-way test, which is this type of Wells type of F test, that is testing is the population means equal when we are not assuming equal variances. Then we have what is called as a Kruskal-Wallis test, which is a non-parametric Kruskal-Wallis ransom test, which is kind of try to also consider are these population means in the same level or not. And once we have more than two subpopulation, there's usually interest to consider which two subpopulation, or let's just say all the pairwise comparisons of which population are on average on the same level with respect to this y variable, and which are in a different level. And because we are kind of then doing this sort of what is called data mining, in a sense that we try to find out in all sort of a direction where we could find a difference. We kind of need to do this sort of a correction for these test statistics, in a sense that testing theory is usually developed to consider one hypothesis in time. But in this case, when we are doing this sort of a pairwise multiple comparisons, we are kind of looking for all kind of direction where we could find. So we need some simple methods or some methods to take into account this fact that we are looking for many directions to find out which directions there is a difference, and that's why we need what is called as a multiple hypothesis testing corrections needs to be done. And one method of doing that sort of a correction is called Tukes-Honest significant difference method. And that can be obtained by using this sort of a function in R, and generally there is this sort of a GLHD function which is able to do this sort of a general linear hypothesis and multiple comparisons for linear models, and more generally generalized linear models. And this is very powerful function to do all sort of a hypothesis testing in linear models. So in our example, we have actually generated y values in 4 different populations from normal, and then we have created here this sort of a model, what is called as a linear model, by using this LM function and call it as a model. And then if we use this sort of ANOVA function for this model, then we can get this sort of a analysis of variance table, where there we have here this sort of a F statistics, which is a value of this statistics of this test, which can be obtained by here. And then there's this sort of a p value, which is very small in this case, which can be obtained by this way, showing us that this hypothesis that for each of these 4 populations, the population mean would be equal on equal size, equal level, is not really holding in these samples we have in this case. Then there's this parallel test for homogeneity of variance, which is in this case gets this sort of a value for test statistic, and p value is like here. So this is really giving us the confirmation that the population variance in a different subpopulation is equal size. So basically we can do our inference just by using these 2 lines of code. However, if we had clearly reject here the null hypothesis of homogeneity of variance based on this parallel test, then one way to proceed is to use this sort of a one-way test function, which is testing again the equality of means, but not assuming equal variances. So this is called as a Wells ANOVA test or something like that. And then we have also this what is called as a Kruskal-Wallis-Rankin test to test if these average levels are equal in all these subpopulation, and this test statistic gets this sort of a p-value. So regardless of which the statistic we are using, these data sets are example, or these generations are examples of situation that in each of these cases we reject the null hypothesis of subpopulation means being equal level. And now that we have actually found out that there is a difference in a population means, in the sense that they are not in the same level. Then we are interested to know, well, which subpopulation are different from each others. And that can be then done by using this sort of Tukey's HSD function, where we need this sort of a model, but this time around model needs to be made by using this sort of a ROV function, which is analysis of variance function. And once we have obtained the model, like given here, then we can use this Tukey's HSD method, and we get these sort of values. And here the last column is what is called as adjusted p-values, and these are the ones that we should use and make an interpretation about is this population means difference statistically significant or not from or are they is this difference statistically significantly different from zero. So if it's different from zero, it means that this for these two subpopulations, the population means are not in the same level. So we would make an inference here that yes, A and B are different, C and A are different. However, D and A are not different; they are pretty much in the same level. Same, C and B are not different, D and B are not different, but D and C again is different. And then we can obtain the same result basically by taking this sort of from the library multcomp, this function glhd. So you need to first install this library, and then using these type of arguments in this glhd function, and let's just put the pairwise as a name for this comparisons. What is done here based on this or using this glhd function, we get this sort of a result again here, the p-values, which are actually the same values as in the case of this Tukey HSD function, but there's a slight difference which is just coming from the fact that when we are doing this sort of numerical calculation, there always comes this sort of rounding up problems and so on. So we can actually now go and look at code in more details. So if we go here, in this time around we again generating a different type of data compared to what was there's an example code. So our result now could be different. So first we do this by using this sort of a lm function, which is really powerful function here in R to do this sort of a analysis of variance, a type of linear model, which means that it is just calculating the really it's first of all it takes as this sort of a subpopulation or as this sort of a control group, and then here intercept means that we have calculated for the subpopulation A the sample mean as a value 4.7705, and then these lines are giving us how much the sample means are really different from this control group of population A, and so on. So once we have done our model, then we can use this ANOVA function, which gives us basically the F statistics and p-value. So in this case, we also would reject the null hypothesis of population means being equal. And here we can get the F statistics, p-value. We can work with the Bartlett's test to see if the homogeneity of variance is holding on. Yes, it holds because the p-value has this sort of a value. And then we can, however, we can use one-way test to consider if the variance is not if they are not equal. Again, using this sort of a test statistics, which has this sort of a value and p-value here, we get a pretty much the same type of inference we would make. However, you should not use this function if everything is right with the Bartlett's test. So if we now really this is holding, then we should just consider or use the testing by using this ANOVA type of way of doing the test. And what lastly, then there's this sort of a Kruskal-Wall test, which gives us this non-parametric test statistics, and its p-value is given here. This is means like, so there's like a first 0.000 10 times, and then after 10th decimal there's 294. And so each of these cases we would just reject the null hypothesis. And then what is interesting is to understand is that which of these subpopulations are different. And there we can use this Tukich HST function, which is given like here, and it would now argue that A and B are different, C and A are different, but D and A is not. C and B are different, and so on. And same can be then applied by, obtained by using this sort of a library multcomp. You have to first install it. I'm not so sure it's not coming with the base installation. And then if you find out here that this function GLHT, then by using this sort of lines, we can make this sort of a Tukich type of inference for these pairwise comparisons. And so it would give us these sort of results, which are pretty much the same as, or they are same as in a case of using this Turkish HST function. Lastly, in this video we can now consider this sort of example 2.2, when we go back for this rat study where it was investigated how much weight gains in rats occur within 85 days when they were exposed to the different amount of recombinant bovine growth hormone. And here are really the data set. It is found in this file, and here is our y vector. Here is actually our interest vector, that is a x1 vector, and maybe then x2 here is a gender or other way around. x1 and x2 is as a gender. We could first consider that case that how the gender is affecting the values of y, and in that case we would actually consider has a gender effect on the average level of y, so that we have two different populations, male and female, and based on this population get divided into two subpopulations. We may assume that the response variable y for each subpopulation, so for in each subpopulation j, the random variable ij follows the normal distribution like given here. And we should use now the Wells test to test the hypothesis like that. Calculate the test statistic and calculate also the Wilcoxon's ransom test. So let us do that first. So it means that we first read the data like this way, and then we do the test in this way. So we use t-test, weight gain, because the gender here is actually this in this rats data, it's given in this form. We must use as a factor gender in our analysis. So this gives us the t-test, actually the Wells t-test, because on default in this t-test function the var equal argument is set as false. So here is our test statistic, which is very large, p-value is very small, showing us that yes, in these two groups, group 1 is probably male and the group is female, the difference is quite clearly different. Of course, it would always be interest to kind of try to plot the data. That means in this case, for example, we would plot the data in this way. It would show us how this observation in dataset has been falling in these categories of gender, and gender being equal to 1 and equal to 2. So it seems like So to me, I guess that one is a male population, so here the weight gain is generally much higher level than in a population 2, which is a female. So that really explains the result here. So that was our question A. So the question B is then that we move to the look how this X1 variable, which is related to this growth hormone level, how those values, or that X1 variable, which kind of defines divides the whole population into the sorry, it's not in a 4 subpopulation, it's a 6 subpopulations. And we may assume that the response variable that for in each subpopulation the random variable follows the normal distribution. And here we now made an assumption that the variance is actually same in these subpopulation. So we could actually here use if we use the test var test, we can then look if the variances are equal in these subpopulations, and they are not really. So this variance is less than here, so that's why the null hypothesis of subpopulation variance being same is rejected, and that's why it also makes sense to use the Wells t-test to test the difference. Okay, here we now, in a question B, we assume that the variance is not changing with respect to the that X1 variable, and we could study by using the Bartlett's test, like this way. Let's do that first. And in this case, there's not really enough evidence to say that there's no homogeneity in variance. So, but we are now looking at the weight gain with respect to this variable. So that's important to understand. For example, that we actually now looking at plots like RPGH and weight gain as a variable which goes to the y-axis. So the dataset looks like this. There's actually now gender affecting, because these values are actually in one gender and these are another gender. These are actually males and females, and that same sort of a division is happening for all values of is immediate in this data. However, when we are just looking at this data with respect to this one X1 variable, then we neglect the effect of gender here. So we have to understand that. However, if we are now doing this sort of a analysis, so we should first create this sort of a linear model by using this LM function, and then if we use the ANOVA function, we get our p-value. So there's not really enough evidence to say that so this is a F statistics and this is a p-value related to this F statistics, and there's not really enough evidence to say that these subpopulation means would diverge from each others. Fine. This is F statistics, we can obtain that. However, we can now plot what is called as a result. That is, if we calculate the sample means for each of these 6 populations and drove them into this data set, then our result would look like this way. So I have used here some graphical things which we will discuss about next time. So these are actually the population means in these six conditional sample means in these 6 different subpopulations, and they were now looking like this. And there's really just one sample means which is going much wider or different, has a different level than than the other 4 subpopulations. However, this difference is not enough for us to conclude that yes, there's clearly difference in sample means, and thus there's clearly must be difference in population means. So null hypothesis would stay based on this F-test. However, I think there's now interest to see that is this the second population on average different from subpopulation 1 and 3 and so on. And that's what is the Tukey's HSD function is doing, is now tries to find out is there anywhere difference, and it cannot really find the difference. So we have to look, for example, these second cases. So there's not really statistically significant difference between these differences. So we are not really able to say that there's a tendency for this subpopulation to have a higher or lower values than others, something like that. So we are just stuck with our previous result, and that was really our C. And now we have basically covered this part of related to the t-testing and F-testing, that is the analysis of variance, and these are all in a situation they are test or analysis related to the situation that we have a numerical response variable and then categorical explanatory variable X.